Okay, so it's very nice to have Bernd Siebert again, and he will talk about, he will continue to talk from yesterday, and so he will talk about structure invariance and canonical wall structure.
Okay, so I went pretty slowly yesterday. Hopefully it felt like this to you as well, but I'm not sure. And I think it was worthwhile doing it. Hopefully it will pay out today. So I talked about log structures quite generally, trying to give a general introduction. The upshot of this discussion is that the log structure on, say, a nodal curve records the rates of smoothing of the nodes and the speeds. You know, we had these equations here. And then I talked about tropicalization. That is a functorial process associating to each log scheme a cone complex by dualizing these M bars, these monoid sheaves of finitely generated monoids, dualizing them to get cones and then taking the limit, and that's a cone complex. So with this example here of the tropicalization of P2, you could just get the fan of P2, and the tropicalization of curves over some log point gives families of length graphs. Okay, so that was the key points here. And I wanted you to note that the tropicalization of a log space is really equivalent to knowing what M bar is. Okay, that contains, so that wraps up all the discrete information. And then I started with log Gromov-Witten invariance, but let's start here again. So the moduli space is obviously, you just take the usual definition of stable maps and put log everywhere. See, one crucial difference is that now a point is not just a point, but it comes with a log structure, so this additional monoid. Then if you tropicalize this, we get this situation we had before, a family of length graphs over a cone. And then together with a map to this cone complex sigma, that is the tropicalization of X. So feel free to think of X as being a toric variety, let's say P2, and sigma would then be the cone complex that you get from the fan. Okay, so the key question here is, what is Q? Because if you don't specify Q, you do get an algebraic stack, but it has no chance to be of finite type, because you can just add on factors of n, let's say, to Q that don't do anything. And the crucial insight here is that the Q should be kind of the universal space for these diagrams. So you take a tropical modulus space of maps of length graphs to this cone complex of a fixed type, and I'll say what a type is in a second. Essentially, you fix all the combinatorics, and that gives a cone. You take the integral points of this cone and dualize. This dualization, sorry, has a slightly different meaning here. This is a harm to n, just noticing this now. And that's called the basic log structure. So I'm telling you that whenever you have a map from a length graph to this cone complex, you do get a monoid, a finitely generated monoid, okay, by looking at tropical moduli. So what's a type? The type, well, just fix all the discrete data you can think of. So that's the combinatorial type of the graph, gamma, from your length graph, the strata of the images of vertices, edges, and legs in this complex sigma, and the contact orders, that's maybe the least obvious, that's kind of the slopes. So the derivatives of this map that we had up here, that was H, okay? Okay, so more than many words, maybe it's most illustrative to write down an example. Let's take P2 as an image. So sigma is just a fan of P2. And then I look at the tropicalization of a curve of a stable log map that looks like this. So what is this concretely? It would be a map that has from, let's say, a one nodal genus 0 curve with 3 marked points. We call marked points correspond to unbounded legs. These are the 3 marked points, okay? So this vertex corresponds to this component. It has a node. This is this edge. And a marked point, this is this leg. While this one is the other vertex. It has 2 marked points and 1 edge. And one edge. So me one node. And the map would contract this component completely. You can see this here because this vertex maps to the interior of this cone, which corresponds to this point, okay? While the other point maps to this ray, and that means that this component will map onto or into this divisor, okay? So it looks like that. And the marked points are forced by the geometry. One would be here, and two other points, of course, lie over this. Now, fixing the type means you want to keep this shape. And that's given, it has two parameters. That's the integral length of this guy, of this distance of these two vertices, or of this vertex from the origin, and then the distance of this leg from the x-axis, okay? So this gives a two-dimensional cone, AB, real cone, but then I take the dual and the integral points, so that's an n squared. Just a, so kind of the dual of these things. So that would be the basic monoid for this kind of stable log map. Maybe I should pause here to give you everybody occasions to ask, because that's a key point. All good?
So how many, so the second bullet point in the definition of type.
Oh, yeah. The strata of the images, right? So you want this vertex not to move into the interior of this cone, right? You want it to stay on this stratum.
Okay.
Yeah. So that would be one thing. Of course, you take the closure of these things, right? I'm describing the interior of these types.
And what's the difference between edges and legs? Sorry.
This is an edge. So yeah, that's an edge and that's a leg. Just in graph theory, right? Your legs are like the edges with only one.
One adjacent vertex means legs.
Sorry, say again? Yeah, I think so. Yes, exactly. Okay. Thanks. So that was already kind of more interesting example. What would you get for the kind of generic point of this modelized space of stable log maps? Well, of course, you get lines, right? Lines in P2, they will be transversed to the toric boundary, so have 3 intersection points, and the domain is irreducible. And the tropicalization is totally boring. Yeah, so you have only one vertex, and then these 3 legs that are part of the one skeleton of this fan of P2. Totally rigid, you can't move anything, so Q is just 0. And that fits here, right? So this is has no nodes, there's no place to put a base log structure. Hey, you could, but it would not smooth nodes or anything, right? There's just no node. Okay, so and then cutting all the technicalities, but it's really not that hard. If you restrict to stable log maps with the basic log structure, this basic log structure carves out a good open substack. I use the script m of x from the stack of all stable log maps. And good means, of course, it's Dili, Mumford, and proper. While the stack of all stable log maps is nothing, neither, right? It's neither Dili, Mumford, nor proper. And then if you're interested, of course, you have a forgetful map. A stable log map is really an enrichment of an ordinary stable map. So the forgetful map to this ordinary stable map space actually is finite. And that has been proved by Jonathan Wythe in 2016. Okay, so the next thing that is really totally different from ordinary Gromov-Witten theory. So the natural base space or base stack in ordinary Gromov-Witten theory is the Ardian stack of nodal curves, all pre-stable curves, okay? And that's it. And that's a smooth stack and has no kind of more interesting structure other than that you know what these loci is. Here we have a much more interesting one, namely we will get a base space that completely reflects the tropicalization. The tropical picture tells you what the base space is. So let me try to give this the thing. I mean, why do we need such a base space? The whole space is not virtually smooth. No, I don't think it's true. It's just wrong, I think. there's no virtual smoothness on the total space, but there will be a virtual smoothness relative to a stack an algebraic stack that fixes the combinatorics. The combinatorics, remember, that is the tropicalization. So how do we get this? From this log space X, you can construct something called the Artin fan. And it works like this. So for any point, schematic or whatever, you get this m bar x, and you construct an affine toric variety. Then you take the stacky quotient by the torus of this affine toric variety, so the spec C m bar x group. That thing is a zero-dimensional algebraic stack. Okay, you just divide out a d-dimensional toric variety by the d-dimensional torus. It's a zero-dimensional, it's pure dimensional algebraic stack. And then you observe that if x is in the closure of y, so y is a generalization of x, you get an open embedding from this quotient, this curly a of x, a lower x, sorry, curly a lower y into ax. Maybe if you don't believe it, look at the thing, right? So let's say we have x equal a2, then there's one point, you take a point on one of the coordinate axes. That, of course, makes the m bar one rank lower. It's an a1. You divide out gm by a1. And y is an open substack of a2 mod gm squared, which is this is the curly a. A0, right? That's the origin of A2. Yeah, so you can see this by just adding a trivial factor of GM to A1, and then you see it's just this A1 cross GM sits open, of course, in A2. So anyway, we get this system of open embeddings, and we take the co-limit. Okay. So what you observe is, I told you that the knowledge of M bar is equivalent to knowing the tropicalization. So similarly, this algebraic stack depends only on the tropicalization of X. It's a discrete, kind of discrete object, just like toric varieties are kind of discrete, but this is even more discrete, as we will see in a second. This is the fact. When I first saw it, I was like somewhat in disbelief, but checking very carefully, yes, it is true. If you have any log scheme, you can look at the morphisms from S to this stack. Actually, I didn't say this, but it comes with a log structure, okay? Pretty obviously from the charts that you see here from the toric varieties. So you look at the space of log morphisms from S to X, and you find that this is totally discrete. Namely, it's the same as morphisms of cone complexes from the tropicalization of S to the tropicalization of X. Okay? So here's an algebraic stack that essentially just tells you what your tropical picture is. And then the base stack you have to work over is often denoted frac M for, in the usual case, to denote the stack of pre-stable or nodal curves. And now it depends also on this Artin fan, curly X. You look at the stack of basic stable log maps, but now not to usual X, but to curly X. So let's try to spell this out in terms of this insight. This is what is this saying? So objects here are still a nodal curve as a domain together with a log structure. Okay, this requires S to be a log scheme. So we need a domain with a log structure. And the only additional information that you have is what once you have a domain curve with a log structure, you have a tropicalization, which is a family of length graphs, as we know, right? It's a cone complex. So you get this guy. And then you want a morphism from your curve to your curly X, which is the same as this kind of map from cone complexes. So the upshot is, apart from the information of the domain as a log curve, the only additional information is exactly this. Oops, where am I? Yep, here is this kind of map. or maybe this diagram. Okay, so that's the only additional information. This is our base space. And this is the theorem that both in the work of with Mark and the kind of competing work of Dan Abramovich and Chilo Chen, there's some statement, maybe not formulated exactly this way, that this is a virtually smooth map. Okay, and we have it explicitly in later papers. So meaning that it has a perfect relative obstruction theory. This guy is pure dimensional of essentially the dimension of the domain, the modular space of domains, and it's a virtually it gives log Chromafitten invariance by pulling back the fundamental class of this guy by virtual pullback by pi. Questions? Let me pause here.
So
Sorry.
Please go. Okay, I guess that's it. So,
okay.
What kind of object is curly X again? Isn't it?
Yeah, it was this weird Artin fan, right? So you take the co-limit of all these quotients of toric varieties by their tori. Okay, so these are zero-dimensional Artin stacks, and then
so it's a limit
maps use open embeddings, curiously, okay, and then you glue them all together.
Okay, so it's a stack, but then you also have an actual log structure on it. Is that?
Yeah, yeah.
So you start with a log scheme X, and then you get another log scheme.
Yes.
X.
Yeah, actually, yeah. So maybe one way to say this, good point. So there's a map from X to curly X. And the log structure on X is induced by pulling back the log structure on curly X. So if let is, what do I call this? Maybe let me call it L, whatever. And then so MX is actually L upper star M curly X. So this is what people call is a strict morphism. Okay. So this really, it's a stack that captures the log structure.
Sorry, Bernd, can I ask a question?
Sure. Well, this is who is it? Oh, this is
you win on the marks.
Yeah. Okay, go ahead.
Oh yeah. Just my question is kind of like basic. It's like instead of considering the map from the modular space of the stable log maps to the maps to the Artin fan, right? We can, because that modular space has a log structure, like basic log structure, you said, right? And we can take a look at the Artin fan of that stack, right? We can consider a map just from the modular space to X to directly to the Artin fan of that stack, right?
Of the modular space, which stack?
The Artin fan of the modular space.
Yeah. But that wouldn't be good enough. Of course, you have a continuation of this map to what you were saying, like the Artin fan of this guy, which is the same as the Artin fan. Well, that is also true, right? So this map is also strict here, okay? So there would be another map then to the Artin fan of M of X, which is the same as the Artin fan of curly M of X, frac M of X. Yeah. But that doesn't keep the information of the domain. And you really, for this perfect relative obstruction theory, you need that information.
Yeah.
You want to fix the domain structure. I guess you could, maybe you could, not sure. Anyway, we don't do it this way.
Okay, yeah, anyway, thank you.
Okay, thanks. Very insightful remark. Something more?
Can you say in words, like what is this theorem saying? What's the difference between MX and frac MX?
Okay, yeah. Okay, sorry. This was a stack of stable maps to stable log maps to the usual X, your target that you're interested in. Let's say P2. This is stable log maps to curly X, which is a zero-dimensional Artin stack, just kind of that looks the same for all, let's say, toric varieties with smooth toric varieties with 3 boundary divisors. They will all be the same, right? It's all the same curly X. Okay, so it's a much more universal object. similarly to like nodal curves in ordinary Gromov-Witten theory. But here we have some information of the maps, but it's just the kind of discrete information carried by the log structure. Okay. Okay, so this point of view, so I'm glad I feel like something got across. That also tells you the natural stratification of logarithmic Gromov-Witten theory. So this also is stuff we only really understood when working with punctured Gromov-Witten invariants. So the strata of curly m, curly m of x, frac m of x, frac m of curly x, which induce, of course, a stratification of the much more ill-behaved, usual, really modelized behavior that you're interested in, the script m of usual x. They're given by the type. Yeah, so recall we had this type in just defining the basic monads. And well, you have to define it kind of schematically, but let's just do it on geometric points. And the geometric points are characterized of a stratum by tropicalizations that contract onto this tau. I'm not going to formally define what that means, but let me just indicate in one example to give you an idea what I mean. Let's say tau is the following type. Okay, we go again to P2, but we do something a little more tropically degenerate. So we just look at this kind of tropical map with this image. Then you can look at the more tropically more generic situation, which we had looked at before, where this vertex moves out, but forcing another vertex here, or you can move in the other thing, in the other direction. Both of these have a kind of contraction map to this type. In the modelized space, that means this guy means you have a P2 and a P1 mapping with 3 marked points, a smooth P1 with 3 marked points mapping to the 2 zero-dimensional strata, and 1 marked point mapping to the divisor. Okay. Now, obviously, this point can move either to this side or that side, and you get a bubble, which could either lie here, and that would be this situation, or the bubble on the other side, which is this situation. Okay. So in this contraction of types, this notion of contraction of types tells you exactly what the strata are. So for each type, you get a stratum of the modelized space. There's a generic kind of point, right? The generic point is kind of this thing. You have just one vertex at the origin that you always have in sigma, and then a bunch of rays that tell you the kind of contact orders of your marked points. So and then you have the various substrata and so on. Okay. So yep, go ahead.
How is a substrata of that, right? Of this most generic one? Is it? Can I?
No, the tropicalization goes the other way around, right? As you can see here. So this is tropically higher dimensional, right? It has a tropically 2-dimensional thing, while this has a tropically one-dimensional. Okay. But this means you go to a deeper point in the modelized space. So it's inclusion reversing, yeah? Just think of toric varieties. Yeah, so the generic point has trivial log structure. You go to a divisor, you get log structure n, and then you continue. And at the 0-dimensional point, you get a log structure of degree. The m bar will have rank equal to the dimension of the toric variety. Yeah, similarly here. Does this answer your question? Okay. Okay, so I would like to say something on these log transverse cases, expanded degenerations point of view. I tend to skip it for now because I'll have a lot more to say. Maybe if we have more time in the end or you are interested, then ask me afterwards, okay? Let's skip it for now. So rather than doing that, let's go to punctured Gromov-Witten invariants. Maybe first a cartoon to motivate what this has to do with kind of pictures you are familiar, or some people are familiar in symplectic geometry and Floer theory. So in Floer theory, you often look at situations where you have maybe 2 repo orbits, one incoming, one outgoing. And so this means you have kind of a positive side and a negative side. So for example, you define differentials in Hamiltonian Floer theory. That would translate in algebraic geometry to a sphere where one point has a positive contact and the other point has a negative contact. Okay, and that's something you cannot typically, no, you cannot do by ordinary Gromov-Witten theory, lock Gromov-Witten theory, because there will always be positive contacts. And punctured Gromov-Witten invariants allow you to talk about negative contacts that you need to kind of have an algebraic geometry, algebraic geometric analog of familiar things in Floer theory, or to define something like relative quantum cohomology and these kind of things. Okay, so how does this go? So we call first that at the marked point P, a log smooth curve, so a log curve, C over, let's say, a log point with monoid Q. What's the log structure at this point? So this is the M bar. So what I mean is this is the M bar, the stock of M bar at P. That's a Q direct sum N, and Q is the space monoid. And this N tells you the vanishing order in the horizontal, in the vertical direction at this marked point. And the map is simply that it maps Q comma K to beta of Q, the beta, the log structure from the base, and then the Z to K, where Z equals 0 is the equation of the point. Okay, so this is something Umut asked me yesterday about, and I try to explain a little better. So then what you observe is one natural operation in Gromov-Witten theory is splitting a node. Okay, so I could have drawn a second component, but let's just focus on one irreducible component. So you can look at this, look at it as a closed subspace of that C, and takes the induced log structure. Okay, so at first you would think, you should get a kind of marked point here, but that's not right. So why is that? At this point, we have an equation ZW equals T in the log structure. So that means that pulling back, it's not generated by two generators, as we should have here, right? The Q would be just an N for the T, and then I have another copy of N, which would be the Z. But you have another one, which is what W was before. And you can rewrite this from looking at this equation as Z inverse times T. Okay, so that's an additional generator, and you see this negative power here. And that should be interpreted as a puncture. So that thing is a submonoid of Q direct sum Z rather than Q direct sum N. It might be worthwhile to look at the monoid picture that you get, right? So Q direct sum N, if this is Q, you draw this in here in the plane, and then you have this additional factor Z in the other direction. Then the marked point would just live in this kind of upper half plane, upper half space, while the W goes down here. And everything like below this plane would have a kind of negative exponent of Z, so that will be punctures. So the formal definition is as follows. You start with a log curve, and I'm defining the puncturing at a marked point. Okay, so this will be, so this comes, your curve with a marked point comes with a log structure MC, and then I can take the groupification with stocks Q group direct sum Z, and the puncturing log structure sits in between these two things. We call this MC circ. And it has the following conditions. First, outside of P, it should just be the same. Well, of course, if you have several punctures, you want to remove all the punctures. And then the M bar, you don't do anything with Q, okay? You only change this this power of Z. So it's a submonoid of Q direct sum Z. And then there's a key condition that you want that whenever you have a negative power, I still want a good map to the ring of functions on C. So whenever this exponent is negative, I want the alpha morphism that goes from MC to OC, or MC0 to OC, MC circ to OC, to be 0. Okay, so let's just swallow this at the moment. What you notice immediately is that unlike the log structure at a marked point, that was a completely universal construction, this puncturing is not unique. It should be obvious by staring at this diagram here, because you could add a bunch, I mean, essentially you can add any kind of finitely generated monoid down here. Yeah, so it's highly non-unique. You can add a lot of generators. Nevertheless, you do get an algebraic stack of punctured curves and a forgetful map, forgetting the puncturing, so turning a puncture point into a marked point, which locally is a closed embedding. That reflects the fact that everything you're doing is completely determined by discrete choices. Yeah, so essentially you have to choose your monoid, your enlargement of your monoid q direct sum n, and that will fix everything. So, but why is it a closed embedding? Shouldn't it be maybe an open map? So here's a key feature and a key difference to ordinary log curves, or why puncturing curves are very different animals than ordinary log curves. Let's look at a curve with equations log structure ZW equals t squared. Okay, so and then I look at t equals 0, so just a nodal curve, one node. And one, sorry, and then actually, sorry, not a nodal curve, obtained by splitting a nodal curve to the component w equals 0 as before. And as long as t is 0, this is a perfect puncturing, nothing wrong with it, right? So this condition here, the red condition is fulfilled. And it's even true still, this curve deforms to ct mod t squared. It's still 0. ZW is still 0. So if you write down, where was it? This W equals Z inverse times T squared, that would still map to 0, right? But then if you go one order higher, that's not true anymore because W becomes Z inverse T squared, and that violates this condition. So you see that by introducing a puncturing, we have introduced an obstruction to deforming this curve to higher orders. While if it was a marked point, there's no such obstruction, you can just continue. Maybe a slightly subtle or technical point, but it's just trying to explain why we do have kind of obstructed deformations of punctured curves without doing anything, right? So that is kind of worrisome from the log Gromov-Witten perspective, where you are used to working over a smooth domain, a smooth space stack. Questions to this? Basically fine at the moment, or any questions?
I connect this to the initial Floer theory picture. Like in the Floer theory, the difference between a plus n and a minus n is essentially, well, I would say cosmetic. I don't know. You choose an n, you choose a different kind of n.
Well, there's no map that would go like this, right? I mean, you can't, there's just no map like this, right? It wouldn't work.
No, I mean, in Floer theory, something becomes a minus curve if you consider it as a negative input. So if you put a negative cylindrical end in there.
Right, but you cannot exchange like negative with positive cylindrical ends. That's a different thing, right?
But there, like, you don't see a big difference between them.
Technically, yes, I agree. I agree. So that's what I'm saying, right? So in symplectic geometry, just this choice of sign, right? So while in algebraic geometry, you always have positive intersections unless you map into something, okay? So that's a problem for logarithmic Gromov-Witten theory. Logarithmic Gromov-Witten theory forces you, without working with punctured curves, yeah, forces you to work with positive inputs. And by the way, that is why Kiel U in this non-Archimedean approach cannot mimic these kind of things. So they have to work indirectly. They only, whatever is a kind of, whatever would require negative input they get around by tacking on something that has positive inputs or something, you know. So that, at least that doesn't exist at the moment in the non-Archimedean approach to have some kind of negative ends. Well, they have some, but they have to kind of, they have to take a way to do this, but it's not directly, it's indirect. Okay, anyway. Right, so let's then talk about punctured maps. The definition is straightforward, right? I mean, now just allow punctured domains. But then there's, like I said, the puncturing is not unique. How do you fix the puncturing? I want that the choice of puncturing is minimal. That means that the log structure is generated by the kind of marked point log structure, the MC, and the pullback of the log structure of X. So whatever puncturing you put should be forced by the target, okay? So then let's talk about tropicalization, because hopefully we all understood that tropicalization is a very important aspect of the whole story that tells you what the base domain is and so on, and the basic log structure. The punctures now turn what were erased before, these from the marked points, into line segments. I would have to write it down. I don't have time to do that. Just believe me, okay? You will get line segments. You chop off the legs. And that kind of thing here, this condition means that such line segment extends as much as you can without leaving your cone. So let me look at this thing, okay? So this would be one punctured curve you obtain by splitting at this point from this kind of degenerate line, okay? So then you have just one component with a puncture that can take any length here. And that condition tells you that this line segment extends to this point. So we are denoting puncturings by arrows, and the arrow, you just extend the arrow as much as you can. You might get a little nervous and thinking that now you have to do something fancy with your types, but actually no. Well, a little bit, but maybe not where you expect it. So this thing here and that thing here, the arrows end at different points, at different kind of strata, but that doesn't affect the type, okay? So these are considered of the same type. But if you move that point to that boundary here, you have a bit of a problem, because at this point, this vector is not a tangent vector in here anymore, right? So there are two choices now. You could either say, I take a tangent vector here, and then you turn it into a marked point. It's a very different type. Or it would be still a tangent vector in this cell, and then you consider it a limit of this type. Anyway, maybe too technical to really to explain properly. But you do get a basic monad, and it's formally the same as before. So you take tropical modular fixed type, you dualize, you take the integral points, that gives you a finally generated monad. That's your basic monad. So then punctured grammar-fitting theory, pretty much the same now as before. So you have a proper Deligne-Mumford stack of basic punctured log maps of a fixed type. And they map to a space of, so an Artin stack of basic punctured log maps to this Artin fan of X, okay? And that's a virtually smooth map. Okay, so but now there comes a moment of anxiety where you find that if you don't, I mean, these base spaces are not generally pure dimensional. So that's a problem if you want to think about how do we ever define invariance if that's not a pure dimensional base. okay? But there's a key insight, namely, if you have the type, if tau is not an abstract type, but the type of an actual punctured tropical map, which we call realizable. So there is one punctured tropical map that has this type. Then this base is pure dimensional, and you can easily compute the dimension. So note here, the dimension of tau gives the codimension of the stratum. So in the end, after some kind of modifications of the theory, everything works out beautifully. We have a nice base change, the base space, frac brave brave frac M of curly X, that has a fully transparent stratified structure in terms of types. And you can get punctured Gromov-Witten invariants by doing a virtual pullback from these strata, pure dimensional strata that correspond to realizable types. Let me pause here again and give some occasion for questions.
I mean, at this point, I can only ask some silly questions. So maybe I just.
These are the best questions. Please go ahead.
So can I think of this introduction of puncture as something like, if you have a holomorphic line bundle that you wanted to define as deeply, then you can take a smooth section, which is transverse, and count with plus minus signs. But if you wanted to do it purely holomorphically or algebraically, then you need to introduce this notion of a meromorphic section.
Yeah. It's exactly this. Actually, somehow I wanted to add this example, but I didn't. So if you look at let's say you blow up a point, you have this exceptional curve of degree -1. Yeah, so, and then you look at P1 mapping into the thing. And you try to make this into a log map. Okay? That won't work with marked points, exactly for the reason you're saying. Because the kind of normal bundle of E is negative, that has no place to go in the log structure for a marked point. You have to introduce a puncture here of degree -1. Yeah, that's exactly the point. And of course, that kind of thinking a little bit about it, that tells you that whenever you have a puncture on one component, you have to map into kind of a divide, or you're, let's say, in a divisorial case. You have to map into a divisor that has negative self-intersection, or where the curve intersects negatively. Yeah, so that, because otherwise you get positive intersection numbers.
Okay, I think I have to think about this example.
I'm not sure if one really wants to, how deeply one wants to understand it from, or can understand it from what I said so far. I think what I want everybody to kind of think of at the moment is that we have this kind of technical enhancement or enlargement of ordinary log Gromov-Witten theory that allows these negative contact orders. And then, okay, so formally that's not so hard somehow once you have the correct definition of a puncturing. And then there is a little bit of thinking about types and tropical geometry, but other than that, it all works as expected. Okay, so it's pretty much analogous to ordinary log Gromov-Witten theory. Yeah, so I have 2 more slides on this thing, but I only have 15 minutes left. So of course, okay, let me quickly go through this before I come to the second part of my talk, which to your relief has only 4 pages, okay? I felt it's more meaningful to tell you exactly what these invariants, or try to tell you something more about these invariants, rather than telling you nitty-gritty details on how we use these. We use them to canonical scattering diagrams. Anyway, the whole point, or the first motivation was not really kind of defining wall structures, but we wanted to understand how log Gromov-Witten invariants behave under splitting and gluing, just as we told told here, that if you split a node, right, you end up with a puncture. So that was the original motivation. And we struggled a long time, almost a decade, in getting this right. So I skipped the frustrations. In the end, it's all beautiful and easy. Let me tell you what we want to do. Let's say we take a degeneration of P1 cross P1 into 2 copies of P2 that exists, has a tropicalization like this on the central fiber. And I look at a union of 2 lines that intersect here. And there is a stable log map with this image. That's C0. Okay. And the tropicalization would just look like that. And then, of course, you can now split at this node. And you would get two curves. Once you have split, of course, this curve can deform away from the other one, and you would obtain some kind of matching condition along this divisor that tells you how to glue. But then one problem, I mean, this is a situation that Jun Lee already solved, because as long as you're on a smooth point, and others, like there's a paper by Helge Rudder and Travis Mandel on Michel van Garel. Sorry, it's not Travis. Sorry. Tom Graeber, and telling you how to do this in log geometry and so on. But then if you look at, of course, in the modelized space, there are situations where this point maps to the deeper stratum, and then this is not covered by these smooth divisor cases. So this would be a non-transverse case that, for example, looked like this. So you could have a 4-component curve with tropicalization like this, and you would, again, like to split here. So this gives all these kind of splitting diagrams with punctures and various types. And then for gluing, again, first you observe that it suffices to do this on the frac M brev level, because we can then use virtual smoothness from the usual modelized space to pull back. So it has nothing to do with obstruction theories, okay? Or rather, the obstruction theory plays nicely with it. That's something you have to prove, but it's true. One problem is that the stabilizer tori change, maybe I skip this, it's a big headache, which means that the natural splitting map you get on the frac M level is not proper. So there's no way to do intersection theory by pushing forward. Chile had the key insight that there's a slight enhancement of the space or modification that makes this map proper. Namely, you get rid of the stacky structure at the evaluation point. So that's the fiber product over frac M with the usual X, lifting this kind of Artin fan evaluation point to an honest point on your gluing stratum, and then you have a nice gluing diagram. Okay, so I'm afraid I cannot properly say this. The upshot is that this reduces the computation of this glued modelized space, virtual class, to computing the push forward of the fundamental class of this guy in here. And Yishan Wu, I should say, Yishan Wu, my student, has a nice paper telling you how to do this if there is some kind of toric action on the gluing strata. And you have beautiful formulas that we use in the canonical scattering diagram formula, canonical wall structure formula. Okay. Are there urgent questions?
I mean,
yep, go ahead.
Yeah, it's just I think yeah, pretty much that's perfect. Just whenever you do a splitting, right? Like take a look at your diagram here. You do splitting, but the question is like once you do like you split a node at a node, right? Then your resulting curves are actually not a just fine saturated log schemes anymore, right? So you kind of need to modify the log structure on the stacks firstly, and then do the gluing. Okay. Something like that.
That is a very insightful remark. But what we learned in all this long struggle is that this is an irrelevant point when it comes to computations. So pushing forward this fundamental class here does not see that non-saturated structure. Yeah, if you look in our paper, we have various statements on this effect. And if you look at Yishan Wu's formula, it doesn't come up. Okay. So if you do it by hand and try to kind of work backwards, like pulling back, you have all these kind of things you have to adjust. But if you push forward and do the computation up here, it doesn't matter.
Yeah. Okay. Yeah. Good.
Okay. So yeah, let's go to the second part then. And it's really only, well, 5 pages. I lied. Okay. So, but we have like 10 minutes. We started 3 minutes late, I think. Okay, canonical wall structure. So my aim is here to tell you, well, to be honest, I hope that Julia would have told you, well, she certainly told you last Friday, or those people who attended her talk. Others can still pull it up from the internet. How to obtain from a log Calabi-Yau situation x comma d a dual intersection complex, and then if you have a wall structure, some kind of mirror. Okay, so this talk will not be about how to obtain the mirror. I'll assume that you somehow know, although I noticed that Julia didn't talk about that part. Well, one can only talk about that much in each talk. But anyway, so you'll have to take this for granted if you don't already know it. So what this part of the talk is about is really, I start from a log Calabi-Yau. I want to construct a mirror. And the key point in my program with Mark is, or the thing we have produced for many years is producing a wall structure, and then via broken lines, the theta functions, and then you get the mirror algebra. Now, here we now have punctured invariance, and we can define the wall structures, which was kind of a miracle of, well, not a miracle, but it was like a wish to understand what these are really in terms of enumerative geometry. And we knew it only in very, very restricted situations to really give an enumerative interpretation of all the functions in the wall. And that can be done by taking one punctured invariance. So an invariant with just one puncture. And then the broken lines, these are the things that pass through walls. Yeah, so like in this picture, you have a wall, and then you have some kind of thing that passes through. This is a tau in, and then you bend by interacting with the functions on the wall. They can be obtained by two punctured invariants. And this scattering process, which is key in understanding why the enumerative things are the same as what you get from just doing algebra, has to do with gluing. So that comes beautifully from Yishan's gluing formula that tell you how to glue on these kind of one punctured invariants coming from the curve carried by the wall to the kind of two punctured invariant for the broken line, okay, to extend your broken line. Very beautiful picture. I'm very happy, or we're both very happy that it came out so beautifully. Historically, let me just tell that the predecessor of all these kind of enumerative interpretations of scattering diagrams is really the paper by that Mark and I wrote with Rahul Pandaripande in 2009, where we had what later became well, where we constructed, kind of did an intrinsic mirror symmetry. Well, the paper is called Tropical Vertex, so it doesn't have mirror symmetry in the title, but it really, together with previous work of Mark and myself, it gives intrinsic mirrors to blown up toric surfaces. Okay, and then Grossack and Kiel generalized this construction to well, in terms of mirror construction, it's a minor improvement, but they generalized to this log-Calabi-Yau surfaces. And anyway, so these are the predecessors, and then of course there's this alternative approach by Kiel-Yu that you heard yesterday. Tony giving a talk in terms of non-Archimedean geometry. Currently, it's still limited. What is available on the internet is still limited to X containing an algebraic torus, but my understanding is they'll have essentially overcome that restriction, and maybe they need that the complement of D is affine or something. Okay, so let me quickly give the setup. So we have an axis projective over C. D is a simple normal crossings divisor, and we don't necessarily assume Calabi-Yau, but maybe skip it. We'll skip it, but it's a lot stronger. Okay, so we need only that it can be written as some AI-DI with non-negative coefficients of the AI. And then there's a way to produce this enhanced dual intersection complex called the Concevic-Solomon skeleton by taking only those DI where AI is actually 0. So these are the ones where your holomorphic volume form has only simple poles, logarithmic poles. So, for example, for the blow of P2 in one point, you can take D with or without this exceptional divisor. And in each case, the Concevic-Solomon skeleton will look like the fan of P2. And then you define an affine structure on B away from codimension larger or equal to from the intersection numbers, or yeah, of one-dimensional strata. They correspond to choices of n minus 1 divisors. So D1 intersected D2 intersected D. Something is wrong here. D2, that should be an N, right? That confused. I think it should be an N. Something I confused myself with some notation. Anyway, so and then you tell essentially how to go through a codimension a codimension 1 cell. So you have to tell how this bends, and there's a formula to do that. You get an affine structure on B, this dual in this Concevic-Solomon skeleton away from codimension larger or equal to. Okay, so that's the arena.
Sorry, can I ask a question? So,
yeah.
So this relaxation means that now you can have simple poles, you can have nothing, and you can have zeros along the divisors, right? That's the higher order poles.
Right. Yeah.
So now, okay.
No, lower. Sorry, this is lower, right?
So I don't know.
Yeah, so that's what it is saying, right? Log D introduces first order poles, and you want it to be larger or equal than that.
So you can have higher order poles.
Yeah.
So then I'm a little confused about.
No, lower order poles. That's what I'm saying. I mean, maybe let's skip it. I'm running out of time. I mean, it's not. We can maybe discuss. Let's focus on the log Calabi-Yau case at the moment, right? Then this is just 0. Okay. So, and then how do we get walls? So essentially, I try to tell you that the tropicalization, which actually is the B of Z, yeah? So, no, that is actually not true. The tropicalization, where is it? The B is part of the tropicalization. That's some of the point of the Concevic-Solomon skeleton. But still, each integral point of B corresponds to a contact order with D, okay? So we can feed this into punctured Gromov-Witten theory. So this is this U, and U will be in some cone, maximal or not, but we only, for walls, we only need codimension 0 or codimension 1 cones. Then we have a homology class of your map and a certain tropical type. And once we have this, we get a virtually zero-dimensional moduli problem and a corresponding Gromov-Witten invariance that I call NAU tau, okay? And you take all these NAU taus in there. Sorry, you take one, for any NAU tau, you get one wall. They may lie on top of each other. So the kappa tau is some lattice index, then you keep your homology class by the space monoid for your deformation, and then some function on your B, some monomial. So these are the walls. This is the wall function. And that gives some definition of walls. And of course, at some point we have to show it's the same thing that we had before. And that will be part of the main theorem. So, okay. So for example, let's just do one thing. Blown up P2 in one point. There's a strict transform of the line between this point and the blow-up point, which is this L. And like I said before, right, this is this -1 curve. It has this one puncture thing. And it would introduce a wall here. And this is one of the things that occur in the paper by Gross-Hecking and Thiel. So I think it's one of the examples worked out in this paper. Okay, so this is walls. And then the broken lines that give you theta functions come from two punctured invariants, right? So we have one contact order which tells you how this is coming in, then you kind of bend maybe, and then you need an endpoint. And so the P will be an incoming point. Well, it looks like incoming, but it's actually, depending on how you do your sign convention, it's a positive input, but the outgoing point may be positive or negative. But it lies in the integral tangent vector of some cell sigma. And then of course some homology class for your curve, some curve class, and the tropical type tau. And then you can define some kind of enumerative theta function at a point Q, some formula involving these two punctured invariants. And then this is the thing I said I want you to take on faith, or if you don't know it already, that the wall structure gives you a formal deformation, curly x0, of the codimension, the complement of the codimension 2 locus of the central fiber that you construct from the geometry, from the topology of your B or the P, this polyhedral decomposition. And that's my last slide. So the main theorem then says that all these logarithmic kind of thetas, they become local functions on patches here, on affine patches of this guy. They patch to give global functions on curly x0. So these define enumerative or logarithmic theta functions for each contact order on this formal deformation. These agree with the theta functions you obtain from broken lines if you feed the wall structure defined by one punctured invariance into the algorithm. Okay, so we have walls that we now produce. We have a canonical wall structure. They give you theta functions by an algebraic combinatorial procedure. We have theta functions defined by log geometry, and they agree. And then you can show that the log theoretic wall structure you produced in step, what was it, 1, is consistent. And finally, the structure coefficients that you get for the multiplication of these theta functions, so they will be like pair of Pan's products, right? So 3 punctured invariants are, as in our previous paper on intrinsic mirror symmetry, where we worked with punctured invariants, but with these 3 punctured and 4 punctured invariants. And that Mark will probably say something about that tomorrow. Okay, so that brings me to 3 minutes overtime. Sorry doing that, but that's the end of the talk, and I'm happy to receive some more questions.
Okay, first let's Bernd. So you're not, this local Avion story, there's no assumption of the laboratory model, right?
Sorry, I didn't quite get this. The log story is what?
There's no assumption that it has the toric model.
No toric assumption.
Okay,
this is very general. I mean, yeah, so just this condition.
Okay, so
we have a little technical condition that has to do with the B, but yeah, to be completely honest, it's a little more. This is the assumption we need in the intrinsic mirror symmetry paper. The canonical coordinate paper is slightly weaker, but there's no toric assumption, no affine assumption. Okay, it's very general.
So I have a follow-up question. So presumably there's some kind of underlying SYZ picture in this story. Hopefully. Now people usually, like at least in symplectic geometry, there's the popular notion of gross Siebert type singularities.
Ah.
Is there any like this?
This predates this work a lot. So what people call gross Siebert singularities in SYZ fibration, that's the stuff we did in our 2003 paper or so, where we had explicit models, or the 2003 together with the paper we came out in 2007, we have explicit local models of singularities. So they are kind of rigid. In a logarithmic from a logarithmic perspective, for example, okay? This one here, well, on the positive side, we don't have these models. Jesus, I'm not a minimal model guy, but the singularities occurring for these guys, or if you look at, I mean, okay, here, yeah, what you get from as mirrors from this guy, I have no idea. Okay, so this is hard. I think you might get very singular mirrors. Okay, we are studying the algebra, and while before with these restricted classes of singularities, we have very fine control of the singularities, but then it's not as general.
So this applies, because
yeah.
this gross from the Siebert paper, they also not about kind of gross Siebert type similarity.
Well, this is just dimension 2, so that is really easy. I mean, Julia had this paper with Mark, this higher dimensional topical vortex that generalizes this to higher dimensions. And they have, there's, if I remember correctly, they essentially blow up Marcus here, right? He can chime in if you want. That they blow up, they blow up devices in hypersurfaces. So that gives also better control. But yeah, no, we don't have that fine control of singularities in this setup.
So in your formula for the wall functions, like maybe 2 slides, yes. So first there's a sum there, right?
No, there's no sum. But that's a matter of choice. I mean, so either you say the walls can agree, and then you have like as many walls as you need summons, or you take the product of all of these, or the x plus the sum. Okay, if you want, you can sum over everything that has the same u or something like this. Okay.
Okay, I understand that. In the classical case, this n is something like 1 over d squared or something, right? The multiple cover contributions give
no, that comes from, how did this go? There was something about the so if you take the logarithm of these things, then you get these 1 over d squared factors in there, or 1 over d and so on.
That's exactly what I'm asking. There's a difference, like in order for getting this 1 plus t kind of thing.
Yeah. write it like this. The exp, of course, is you have an exp, right? So that brings in all kinds of factors, and you can trade.
You get like 1 squared, which you first multiply by d. I don't know why. I never understood why, and then you have to exponentiate.
Yeah, I'm not. One would have to look at the precise formulas. I think it has to do with this, maybe with this evaluation map thing here.
Is this kappa that's does it explain this multiplication by d? Cancels the d in the denominator. Is that somehow?
Yes, it does.
Those offhand, Mark, do you?
Yeah, it does explain.
Okay.
It explains.
In the two-dimensional case, it will just be k-tile will just be the order of tangency.
And that was a d in that. Okay.
K-tile will come out.
Yeah. Okay. Mm-hmm.
Okay.
Any other question from the Zoom? Or from the Zoom? Any question from the Zoom room? Okay, let's take Bernd again.